Okay, so in this example, we're going to look at a situation where we have an object falling with air resistance, and we're going to make the assumption that the air resistance force is directly related to the velocity. So a constant times v gives you the air resistance force. So we want to start out by looking at the diagram and writing out Newton's second law for that situation. So we have ma. I'm going to call the downward direction positive since it's moving downwards. So I'm going to have mg minus bv. Now the thing that I have to recognize is that the bv term there, that force, is not a constant force. It's dependent on velocity. So we have a differential equation here because the velocity depends on the acceleration and the acceleration depends on the velocity in this situation. And we know that acceleration and velocity are related by a derivative. So I can write it this way. So I'm going to write m times dv over dt equals mg minus bv. So if we're asked to simply write the equation of the differential equation that describes the system, this would be it. If you think about it, before we go any further, we could also look at what would a graph look like of this scenario, and we kind of know already, if we sketch it, the velocity as a function of time is going to, if we call down positive, it's going to speed up, but it's going to speed up by less and less because that air resistance force is going to get bigger and bigger. So as a result, it's getting faster and faster and faster, but it kind of levels off and it approaches what we call terminal velocity. And the terminal velocity is the fastest it would go, and that's when the air resistance force equals the force of gravity. So the next thing we could think about would be to actually find that terminal velocity. It's pretty easy to do. We know that the acceleration would be 0 in that case. So the left side of our equation is 0. We have mg minus b times v, and I'm going to put a subscript t here for the terminal velocity. We'll add bvt to both sides and then divide by b. So we get that the terminal velocity is mg over b. So that's an important result. Okay, now if we are asked to solve the differential equation, let's go back to what it was. We have m times dv dt equals mg minus bv. So this is what we call a first order separable differential equation. So what I'm going to do first is I'm going to keep dv dt on one side. Okay, and I'm going to do, I'm actually going to back up here. So what I'm going to do is I'm going to multiply both sides by dt to get dt on the right hand side. I'm also going to multiply both sides by 1 over m and divide both sides by mg minus bv. So a lot of stuff going on here, but just some algebra. So we're going to end up with dv over mg minus bv equals, we have 1 over m times dt. This is going to be the easiest way to solve this differential. There's a couple different ways you could do it, but this is the easiest way. So we have it separated out. Now we're going to integrate both sides. So we're going to integrate the left side and also integrate the right side. Okay, so the right side integral is definitely pretty easy to do. We can pull the 1 over m out and have the integral of dt, and that gives us 1 over m times t plus a constant. So that side, not so bad. The left side, on the other hand, is definitely pretty tricky. This is a tricky integral. So what we're going to do is a technique called u substitution. We're going to try to simplify this integral by using a technique called u substitution. So I'm going to introduce a new variable. I'm going to call it u. And I'm going to say that u is equal to mg minus bv. So if that's the case, the next thing I want to do is take u's derivative. So I'm going to do du dv. So the derivative of u with respect to v, look at this, mg is a constant, we have negative bv. So the derivative with respect to v is just b, negative b. And then the last step of the u substitution is to solve for dv, the d of the the original variable. So dv is going to be equal to negative du divided by b. Now what we'll do is we'll use this substitution stuff in that integral to make it simpler. So check out what happens when we write it. Now everywhere I say dv, I'm going to write negative du over b. So I have negative du over b. And everywhere I see mg minus bv, I'm going to write u instead. So this is my new integral. Now that seems sloppy right now, but we can clean that up pretty easily. It's just some algebra here. So what I have is the integral of negative 1 over b times du over u. And I can pull out the negative 1 over b because that's a constant. So I'm going to do that below. Negative 1 over b times the integral of du over u. And we know that that is natural log of u. So we get negative 1 over b times the natural log of u. We're not going to do the plus c because we already did the plus c on the other side. We'll take care of both constants together. This also has a minus sign, like so. And the last step of the u substitution is to put mg minus bv back in for u. So we have negative 1 over b natural log of mg minus bv. Now that whole mess is equal to what we got on the other side, which is 1 over m times t plus a constant. Okay, so at this point the calculus is done. It's a whole lot of algebra to get us to the end. Okay, so we need to clean up the algebra and basically get v by itself, and that's going to take several steps. Okay, so what I'm going to do is multiply both sides by negative b. So I end up with this, ln mg minus bv equals negative b times t over m plus, now technically this is going to be negative b times c, but b and c are both constants. So a negative b, which is a constant, times c, which is a constant, is just a new constant. So I'm just going to call it c and leave it there like that. I know that's a little weird combining the constants, but that's what we're going to do to keep it simple. Now we have the natural log of this mess on the left, so we need to exponentiate both sides. So you want to imagine e to the ln mg minus bv equals e to the negative bt over m plus c, like this. Now, the left side, e to the natural log of something just gives you the something. So we have mg minus bv equals e to the negative bt over m plus c, like this. I'm going to carry this over here so we have some more room. Okay, the left side we're going to keep the same for a second. The right side I'm going to separate. E to the negative bt over m plus c is the same as e to the negative bt over m times e to the c because of log rules. Now here we go again with the constant craziness. E to the c is a constant because c is a constant. So I'm going to call this mg minus bv equals k, a new constant, which is e to the c, times e to the negative bt over m, like that. Okay, now I'm going to bring that to the left and bring bv to the right. I get mg minus k e to the negative bt over m equals bv. All right, so I could solve for v now, but it's going to make the constant a little sloppier, so I'm going to actually apply the initial conditions now. Initial conditions. And that is, at t0, the velocity is 0. In other words, it starts from rest. So if I do that in this case, I have mg minus k times e to the 0 over m. So e to the 0 is 1. This is 1 equals b times 0, because v's got to be 0. Okay, so if we look at that, that means that this here, k times 1, has to give me mg, which means k is mg. So next step, mg minus mg times e to the negative bt over m equals bv in general. Okay, now on the left side I can factor out an mg and bring the b over. So I end up with this mg over b times 1 minus e to the negative bt over m equals v. And that is the solution. If you take a look, it makes sense too, because it's going to approach terminal velocity as time goes on. And we came up with the terminal velocity earlier when we did this part, mg over b. You can see that the mg over b term is in there. Okay, and it is approaching that value by less and less and less every instant of time is what's happening in this case. So it's a complicated derivation. You have that u substitution in there, which is new for most of us, and definitely some crazy log rules that we need to apply, but it can be done.